So now comes the theory part of things. So pay close attention. It's not that. So we know the time series model YT, the simple case, A times xt plus b plus epsilon t, and t equals 0, 1, 2, dot, 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 up to n different time points. That is our model. If that were to be IID, I don't have to model the noise part. But since it is correlated, if I understand how the noise is correlated, that is the deterministic part, I can add them together and come up with a good prediction. Do you agree with me? Do you want me to continue? So this is the deterministic part. That is a random part. Our objective is to model the type of correlation of epsilon t. So if I understand what epsilon t is about, this is a deterministic component, and theoretically speaking, I can put them together and come up with a good prediction. In practice, though, that part has a bit of variation, and that part will be fit using linear regression, right? So if you have random data, I could fit this using linear regression, AX plus B, and this using time series. Put them together, got a time series model, I can make a prediction. Does that make sense? Okay. So how do we understand the correlation and its type? So correlation is a word that we would keep on hearing until the end of the semester, because all of the time series is about correlated noise. So it's going to keep on coming. So if we want to understand correlation, the first thing we've got to understand is expectation. Let's say xt is a random variable. In other words, it is a value that we measure for x at time t. And that time, 0, 1, 2, 3, and so forth. Or it could be continuous. Continuous case is what we call a stochastic process. Suppose xt is a random variable, then that is notation. So some like to use square brackets, some like to use parentheses. I don't know what your book uses. I kind of go back and forth, but when it comes to expectation, though, I always go with square brackets. This simply means expectation of xt. And you may wonder, well, what is this? This simply is the theoretical mean. Going back to 2023, theoretical mean, it's the unknown mean. The quantity that is unknown in the population is the parameter. And how do we estimate the value of the parameter? We make use of a sample. So, and that is what we call the statistic. So what is the equivalent sample statistic? Before I even write this, let's say you have 10 numbers, and I ask you, what is the average of those 10 numbers? What would you tell me? So let's say those 10 numbers are called x. We found x1, x2, all the way up to x10, and I ask you, what's the average? How do you find it? Add them all together, divide by 10. So if it's an arbitrary n, so you're going to add all n values and divide by n. So watch carefully. This I'm going to write as some. Have we seen sideways n? That means sigma, uppercase sigma. If you're in a fraternity or sorority, you probably understand it right away. I'm sure that went to. One of them got in trouble. What they did, I don't know. Well, I used T, so T. Right? I'm summing all the way up to n. This simply means x1 plus x2 plus x3 divided by n. And that is simply the sample mean. That's our standard x bar. Do we remember x bar? It's the average. So expectation is the theoretical part. This is the corresponding sample part. So this is how we're going to estimate its value. So what we're going to do in this class is make use of the theoretical part to come up with all kinds of formulas. But we know whatever formula that we have is theoretical. If you're going to use a sample, we will just get its estimate. Does that make sense? But it all goes back to expectation, which is why we've got to know this. And if we know this and we've come up with the formula, we can use these to find the corresponding value. Good. Okay. Few reasons, main reasons as to why we have to study about the expectation, the mean, and the variance and correlation. If you go back and look at what I wrote when I compared linear regression to time series, noise is from a normal distribution. It has a specific mean, so we've got to know about the mean. It has a specific variation. We've got to learn about the variation. Time series is correlated. We've got to know about correlation. Does that make sense? We need to understand those three items, and if we don't understand those parameters, we can't model epsilon t. If we can't model epsilon t, we don't understand where the hurricane goes, and we will die. Does that make sense? So, I mean, oftentimes we predict, and sometimes it doesn't work the way it's supposed to. But last time, I believe, Irma, it behaved pretty much exactly the way they projected. So it just happened 95 out of 100 times. Simple properties. These are things that we need to know for this class. Of course, there are plenty of others. I'm not going to get into all of those. You don't need to know. So let's say that A is a constant. Of content. So if we have to find A, X, T, that would simply equal to, you can easily pull out the A and write it as expectation of X2. Think of algebra. If you have a common factor, you simply pull out that common factor. Same logic. Let's say C is a constant. Let's use some practical sense and see if this property makes sense to us. Expectation of C is the same in a sample sense, the average, right? And C is a constant. So if I took 10 values for X, all 10 values are the number 2. So what is the average of those 10 values? 2, right? That's exactly what we're trying to say. Expectation of a constant C has to be C. C. Didn't get the joke. C.
I have read of mine.
Huh?
I have read of mine. It's too early. Okay.
It's not you recording this, but that the jokes are awful. We use the same logic, expectation of AX plus B. You can distribute that expectation, split it up, and write it as expectation of A multiplied by XT plus expectation of B. And they are constants, so that last part would simply be B, and I can pull A out. Something very important. So this is the value of the random variable x at time t. Value of the random variable x at time t plus k. Okay. So for k could be any value. K could be 1, k could be 2, this could equal I was able to split up an expectation directly over here, right? That's called the linearity. So if you had a whole bunch of terms added together, you can distribute that expectation and find the expectation of each of them. But if they are in product, what I did there is I distributed and took the expectation of x of t, expectation of x of t plus k, multiply them. It's fine only if x t plus k and xt are independent. In other words, whatever that happened at time t has no effect on whatever that is going to happen at time t plus k.
I mean, if they're being multiplied together, though, does it make it dependent on each other?
Okay, so 2 times 3, 3 times 2, right? I can do that easily, because those two numbers are independent, right? They are numbers in and of themselves. But let's say xt is some random value. Xt plus k is also some random value. Give me a random value. 4. Give me another random value. 6. So 4 times 6, 24. 6 times 4, 24. But if I said whatever value that you pick has to be 5 units apart from whatever value that he's going to pick, maximum of 5 units. Pick a number, 3. Only 5 units on either side, so he's going to pick A. So you could pick any value between also, but A. So whatever number you are giving me is dependent on what he just gave, right? So in that case, things are dependent. So whatever happens at time t plus k is dependent on t. Good. Here is the bigger question. Would we ever encounter a scenario of that sort in this class? No. Because from the get-go, I said time series simply means noise is correlated, and whatever happens at time t plus k is going to depend on the previous times or some arbitrary time t. So this is a case that's very trivial to time series. So we just can't, write it this way. Life would be way too easy if this was the case. When it comes to time series.
So we have to just leave it as the original thing, or do we want to?
Very good question. We'd have to leave it as the original thing, and I'm going to get into that. Good so far. I'll try to put some homework problems in these so that you have good practice. We want to understand mean, we want to understand variance. Both of them are important. So what is variance of xt? We write it as variance of xt, which should be equal to sigma squared. And I'm going to write the formula now. Good. So mu is the mean, the the unknown name, the parametric name, and I forgot t, so accept t minus q squared. And that is a formula for variance. So I want you to use that technique that I showed you up there and write a formula for sigma squared using the sum. Remember how I went from e to the sum? Let's see if you can go from e to a sum. I'll give you about 2 minutes. So, any thoughts as to how we can go from here to a summation version using a sum? What did we write? Let me quickly see. Halfway, okay. Halfway, that's what I got scrolled about. Okay. Okay.
My brain broke.
Okay, so let's see. Last slide, right? So the entire part, I rewrote it as sum t equals 1 to n x t, and then I just divide it by n, right? Now look at it and tell me, what did that change into? It morphed into something else. Division of n is that it then? Also this funky sum. Yes. Yeah. So this part got replaced by that. With me. Now, a couple of minutes, let's see if we can get it. Well, I want you to understand the notation because I don't want to get confused later on. So the theoretical variance going to leave that part as is, and whatever that I boxed up, I'm just going to replace it by a sum. So I'm going to write it as sum t equals 1 to n divided by n. And what did I leave behind? X sub t minus mu squared. That's it. Now let's ask me a question. Should it be just n? It really doesn't matter. Just like how we brought the constant out, I can rewrite this as 1 over n sum t equals 1 to n x t minus mu. Same thing. Any constant you can put up. And mind you, this is a theoretical variance. In other words, it's the population variance. This is not the sample version. If that is the case, what was the sample variance? We denote it by S squared. If you go back and look at undergraduate textbooks, its standard notation is S squared. So that's going to remain as is. What did I denote the sample mean by? If I'm going to talk about the sample variance, if I'm going to compute the variance of the sample, I have to make use of the sample bit. So what is the sample bit? X bar. So that will get replaced by X bar. Now, if you connect those two, what should go out here? 1 over n. Now this is where things are going to get a bit tricky. It's actually 1 over n minus 1 for sample variance. There are theoretical reasons for this. I'm not going to get into that, it's like other little stats. But here it's n, there it's n minus 1. Do you see how n's went from here to there? This tiny little detail is something I can't cover in this class because you need to know other things. Are we clear with expectation? The theoretical part and the sample part. Variance, theoretical part, sample part. Again, why do we need the theoretical version and the sample version? The goal is to make all derivations, and theoretically we can say, okay, this is the derivation for, these parameters in a time series model, and theoretically this is what I expect. And if our sample series follows a similar pattern, then I could take the theoretical version, rewrite it in the sample version, use our sample values, and fit a model. Does that make sense? So all of these, they are meant for derivations and such. Are we clear?